Section 15.1, and we'll be converting binary to decimal, decimal to binary, and binary to hex in this particular section. And we alluded to this in the first section, but we will review parts of it again. It is important to be able to convert binary numbers to their decimal equivalent. To convert a binary number to its equivalent decimal value, multiply the weight of each column by the digit value in that column. Then sum the products obtained. And we have done this before, but here we have a binary value, and we want to convert it to what is the decimal equivalent. So if we write out the values of each digit, so it would be 1, 2, 4, 8, 16, 32, 64, and 128. And then if we sum those values, then we'll have a 1, and we'll have an 8, and a 16, and 128. And so if we add these up, let's see, 8 and 8 is 16, plus 6 is 22, 23. 3 carry the 2, and we have 5, and we have 153. And we could confirm that with our calculator. If we look at our calculator here and go to decimal and type in 153 and then click on binary, we should have 100110. Okay, and that is the correct value. Okay, so that's binary to decimal. And then we'll go to decimal, converting decimal to binary. If we have a number expressed as decimal number, we should be able to convert it to a binary number. One procedure for decimal to binary conversion is divide the decimal number by 2, write the remainder down as a bit in the converted number, beginning with the least significant bit, LSB. Repeat the first steps until the quotient of 0 is obtained. Okay, this is quite simple actually, and we'll show an example here. We're going to convert 100 to binary, and so the procedure is to divide by 2 and keep the remainder. So if we start out with 100 and we divide by 2, that would equal 50, and we have no remainder. So we would put down the 0 here, and that would become the least significant bit. Then we will take 50, divide that by 2, and that will give us 25. Again, remainder of 0. We'll keep the 0. Then 25 divided by 2, and that would be 12 with a remainder of 1, and we will keep the remainder, which is 1. Then 12 divided by 2 will give us 6, again another 0 remainder. And then 6 divided by 2 will give us 3, and that will give us another 0 remainder. And then 3 divided by 2 will give us 1 with a remainder of 1. So we'll keep the 1. And then, let's see, then we will have 1 divided by 2 is going to be 0, but we'll have a 1 as a remainder, and we will keep the 1. Now, we can evaluate this. Let's see if we do our method here of 1, 2, 4, 8, 16, 32, 64. If we add up the weighted values here, we will have a 4 and 32 and 64. And if we add up 4 plus 2 is 6 plus 4 is 10, carry the 1, and there we have it. And that would be 100 base 10. And so we took the 100 and we converted it to binary. Now this is the method that is addressed in your textbook. I have a preferred method that I like, and this is not in your book, but I just like this, and I mentioned this in the previous section, where I just create a block or a table, and I write in the weighted values, and it would be 1, 2, 4, 8, 16, 32, 64, 128. And if I want to convert this to binary, I simply fill in the blanks and subtract. And so we would not need 128, it would be a 0 here. We would, however, need 64. So I'd put a 1 here, go over here to 64, subtract 64 from 100, I would get 36. And I would need 32, so we would go subtract out 32, that would remain left with 4. I would have a 0 here, a 0 here. I would need the 4, so I'll put a 1 here, subtract out 4, and that is 0, and I'd have 0 and 0. And this should be the value that we just 110100, and that is in fact what we had there, 110100. So that is my quicker method. Do whichever method suits you. Converting between binary and hex. To increase the efficiency and simplicity of working with binary numbers, they are often converted to hexadecimal or base 16. Conversion between binary and hexadecimal is simple. Begin at the radix and mark off groups of 4 binary digits. Okay, the radix, if you had a value, say you had 1001, 1101, and the radix would be this point here, just before we go to the decimal, and we'd mark off 4 digits here, 1, 2, 3, 4, and then mark off 4 digits like that. Replace each group of 4 bits with the hexadecimal digit, and we'll look at the table for what those values would be. So here we have the decimal number, okay, 1, and this is just going up to number 15. And here are the hexadecimal equivalents. And hex is, remember, hex is for 16, and this simply means these are base 16 numbers, hence base 2 or base 10. And we call it hex because there are 16 values, and so we would go from, we would start at 0, and we would go to the letter F, and F is equivalent to 15, but remember we have a 0, so that makes it 16. And in hex, let's see, hex looks just like decimal up to number 9, but then instead of having 10, we will have the letter A, and then B for 11, C 13, and up to F for 15. And then these are the binary equivalents over here. Now, let's do some of the conversions that they had mentioned. We're going to convert these binary values to hex. And so the methodology is simply to group them in groups of 4, starting at the radix. So right here, we would go 1, 2, 3, 4. So this would be one group, and then this would be the next group right here. And so what we would do is we'd evaluate the 4 digits that we have isolated. So here we have, this is going to be equivalent to the number 1. And these 4 digits, okay, if we did the 1, 2, 4, 8, this would be 15, but in hex that would be F. Then here we have, again, we would do the same thing, 2 groups of 4. And so this would be, what, 1, 2, 4, 8. What's this is going to be? 12, 13. And in hexadecimal, that would be a D. 1000, that would be an 8. And then this one here would be, this one's kind of easy. This would be F. F. Now, one of the things that it mentioned a couple screens back was that this simplifies binary. And students always kind of look at me dumbfounded, well, how in the world is this simpler? Well, the simplicity is simply that for every 4 bits of binary, you can replace it with 1 bit of hex. And so in all of these cases, here we have 8 bits of binary, and we have replaced it with 2 digits of hex. Something to keep in mind is that your computer does not use hex. Your computer uses binary exclusively. Hex is just there to make it easier for the user. And if you go into you don't typically talk in hex, but if you go and, for example, if you see memory addresses in your computer, they are always represented in hex values. But I'm departing. Let's check out our calculations here. Let's pull up our calculator just to make sure that we have done this correctly. And the way we would do this, and by the way, I would mention that Windows has a calculator built into it that you could use for this function as well. So let's go over to, let's click on hex, and then and notice you have a new row here of values you can click in. So we'll say F and F1, and then if I click on binary, that should be this value. So it's 1111, and that is in fact correct. So then let's go to the next one. The next one is 8 and D. Click on binary, and there we are. We've got that one. And then the final one, hex, and we go FF, and again click on binary, and it should be 8 ones. Okay, this has been a quick introduction to calculating and converting numbers between binary, decimal, and hex, and here we have gone from binary to hex. And let's see, there was our table of decimal, hex, and binary, and we did, okay, this was a decimal to binary in the method that I prefer. This is decimal to binary using the divide by 2 method, which is the one that your book uses. And then we did decimal to binary. We should know that by now. And that completes our conversion section.